Okay, so microphone is working, so let's all get ready for the talk. So this is a talk which is actually the main work by the master student Stephen, who got supervised by Herman and me. And I shall be presented because there's no Stephen here, so guess you have to do with me. So what is this talk about? Well, we saw the title, we heard Kenji, Impredicative Encodings. So that is what we shall be talking about. So what is the idea of impredicative encodings? Well, we could be looking at some system. We might have a bunch of inductive types, and we take them and we reduce them to more elementary type formers like pi types and function types. Okay, sure. And this is something you might not see anymore nowadays because Waste-proof system still uses this. But if you have history books, then you might know that this is still, that this is how one would have implemented them in the rock-proof systems, although back then the cork-proof system in the past. And this method is something that one would only use in an impredicative setting, which might be why we call them impredicative encodings. So what is this whole impredicativity about? Well, it is this action. So we have this universe U, scary chair. We have this universe U. We're allowed to quantify over whatever type we have in the domain and remain within this universe U. Might seem very scary because if you think set theoretically, nonsense. But this is perfectly consistent to assume if you use stuff like assemblies. So perfectly nice. But you might wonder, why would one want this action if not just for the purpose of angering people who are predicatively minded? What can you do with it? Encoding data types. And let us look at an example. So for instance, the canonical example of list. How do we encode it using impredicativity? So we take this whole pi type, where we basically write down the recursion principle of list, and we quantify over U, and this gives us an impredicative encoding of list. And this is still, basically we have the things that you would expect, because we can define the nil thingy, because for nil we need to make some whole weird function, and we can do that because we have this argument n. We can make cons, because, oh, we also have the C, so we can make cons, and got it? And we can also do construct a recursor using the fact that it is impredicative. Because when we do recursion, we quantify over U. We have this list L, and because this is defined using this whole pi type, which remains in U, takes a first argument, something in U, we can define a recursor. Did you have a question or? There's more reasons to hate these encodings. And thank you for introducing the next slide to me, because this is whole a lie. Thank you. And I did not bribe you. I didn't even have to give you any money to do my work. Because the problem of this whole stuff is that I'm talking about inductive types. And the thing about inductive types is that we want induction principles, and we don't have that. So this previous slide was just a complete lie. So this is something you can indeed show that that is what Herman did. And we can only get like some kind of recursion principle with beta rules, no inductions, and everything seems destroyed. But we shouldn't be too worried, because once upon a time, Steve Audi and Jonas Frey were supervising a master student who was in the audience, Sam Spade, and their message was, we can fix this. What is their idea? This fake lie list type that we just created has too many inhabitants, which is not something we might want to say anymore with the current political state. But what they did was they took this list type and they threw out all of the stuff that they wanted in it. So what they did is they defined a suitable predicate on this list type. They took a subtype and, oh, we can prove initiality. We get induction. So let's remember what Sam told us many years ago. And this time it's me who's telling this and not Sam. So the idea is to basically give some kind of alternative formulation of initiality and encode that. So we're going to define a predicate on lists that from which we can kind of directly prove initiality. So what is this predicate and how shall we visualize it? So let's first just think in diagrams, because who doesn't want diagrams? So let's say we have two list algebras, X and Y, with suitable operations, and we have a morphism between them. So we have a whole commutative square like this. Then what does Sam tell us? Well, a list satisfies this predicate if it makes this lower triangle here commute. So what we have to note here is that here we make use of the recursion principle of the lies, and that we say, oh, a list satisfies this if this lower thing made out of lies commutes. We can turn this into many words because who doesn't like words? So suppose we have an X in U together with suitable operations, and the same for Y. We have a function making this whole diagram commute. Then this L satisfies this predicate if we have this equality, which was exactly what this lower triangle was saying. And now we have this amazing, beautiful slide, much better than the previous one. So Sam just didn't look at a list. He looked at much more, like sum types, algebras for functors, natural numbers, circles. And it also was studied in a setting without uniqueness of identity proofs. But they had to always screw around with all kinds of truncation stuff. Like they were always not looking at the whole imperative universe, but only at those types that are sets. So this is something that is a bit annoying, but there was another master student on Earth, Xavier A. Sylvester, I don't know how to pronounce his name, supervised by two more members of his audience, Benno and Daniel, who said, okay, we can actually do better and use some kind of way to get rid of this truncation assumption. But I shall not be talking about this. I shall flip it all around and look at the dualization. So how can we do co-inductive types using this whole imperative stuff? And that is basically the work that I shall be presenting now. So how can we do co-inductive types using imperative encodings? So if you think about co-inductive types, you might say M-types. But M-types, if I'm going to demonstrate how to work with M-types, that is not something you want to do on a Friday morning. So we shall just be looking at a simple example, namely streams. So I will just show how you define streams using imperative encodings. And if you want to know the M-type case, then you should read the paper and not look at this talk. So what is the idea? If we encode lists using an imperative encodings, we have two ingredients, pi, sigma. An imperative pi and a sigma to take the right subtype. We're going to dualize this. Pi becomes exists. We need to take imperative whatever into account because of imperative encoding stuff. And we dualize subtypes using quotients. So in order to dualize this whole stuff, we need to have suitable existential types and suitable quotient types. And we shall start with the existential types, define fake streams. Then we shall discuss quotient types and define real streams. That is the order in which I shall be describing the construction. So let's start with whatever types. So I will only describe the things that we will get from it. The construction of these existential types is again using imperative encodings, the same way as Sensei told us in the past. So what do we get from this existential type? So suppose we have some type family on U, then we got the existential type, which lives again in the imperative universe U. We get a pack operator, which is like the introduction rule for existential stuff. And we get a rec operator, which is like the elimination rule. And this satisfies both beta and eta rules. So these betas are things you get for free or usually with imperative encodings. And for the eta rules, we need to call Sam, who provides them to us. So this is the first ingredient. So how are we going to define the nonsense streams? We're going to use the existential. And this is the format that we shall be using. So a stream is given by a type X in the imperative universe U. So this X represents like the type of states for the stream. A stream has a current state, which is given by this X. If we have some state, then we can take the head. The heads are valued in E. So this is given by a function X to E. And we have a tail stuff that goes from some state to the next one. And if we take this definition, then we can define the usual things that we would expect from stream, namely the head, tail, and co-rec. So basically how these are defined. To define head and tail, we take some stream, we rec it using the recursion principle of the existential type, because we have that. And for the co-rec, we've turned it around. Rather than destroying some stream, we pack it by putting stuff together. Because we're given some type U, some kind of function X to E, a function X to X, and then some X, and then we can construct a stream by putting this all together. But this previous slide was a lie, which I keep saying, because again, we do not get a suitable co-induction principle. And to fix this, we're going to take a quotient, dualizing this idea of Sam to take subtypes. So again, I can discuss quotients using all kinds of imperative encodings, but time is limited. So I'll just say what we get. So we can construct quotient types given like an X in U and a relation valued in the imperative universe using imperative encodings again. And what we then get is some kind of quotient in U. We get a class function satisfying the usual initiality principle that one would expect from quotients. And the beta is just what one would usually get from imperative encodings. The eta is the one that requires the trick. So if we're going to fix the imperative encodings for streams, we need to again look at this additional requirement we gave for lists. So what we did for list is we want to say, oh, we are only going to pick the lists that make this lower diagram commute. This is what we must flip around. So what we in essence want to do is suppose we have two co-algebras, X and Y. We have a co-algebra homomorphism between them. Then we want this upper triangle to commute. So we want to define an equivalence relation on the lying stream so that we can guarantee that this upper triangle will commute. And now we can ignore the boring diagram and we can start looking at interesting formulas, because who doesn't want to see long formulas? So let's say we have two streams, sigma and tau. We identify them if there are x, y that are co-algebras. So we have suitable hx, hy, tx, ty. If we have a function f that is a co-algebra morphism, meaning that it preserves both the head and the tail. And if there's something in x that, if we think back about the triangle, something in x which was in the lower left corner that gets mapped to the sigma on this leg and to the tau if we take this route. So correct x, the capital X applied to x, correct y applies to fy. And if we define this equivalence relation on, or if we define this relation on stream, we can take a quotient, and that allows us to prove the co-induction principle, and we get a perfectly nice stream type. And this idea works perfectly well for M-types. It is just, the only difference is that you have to punish yourself more because you have to use arbitrary polynomial functors rather than just the stream things. So all of the impredicative encoding stuff, as discussed by Audi, Freyt, and Spade, works perfectly well for co-inductive types as well. The only change that you have to make is that you need to use existential types and quotient types. And that's it.